I'm James Tagg. I'm going to talk to you about quantum computing, in fact quantum gravity computing, just to be a bit fun. And I'm going to do three things: the background motivation for why you'd want to do this, a report on our experiment, which we've been running for some time now, and just a discussion about what's involved in making a quantum gravity computer. What's the motivation for making a Penrose-Hameroff ORCH-OR quantum gravity device? If you find a way of unifying general relativity in quantum mechanics, you're almost certainly going to have to change the Schrödinger equation. If you modify the Schrödinger equation to make it nonlinear, then you get the ability to make a computer that's more powerful than a Turing machine. Now, Scott Arison was asked about this, and I'm totally paraphrasing him here, but he basically said if you make a machine that's more powerful, you get a ridiculously powerful machine. A bit like, the monster from the Forbidden Planet, the Tempest, where it can do anything. My argument with him is that can't we have just a tiny bit more power without actually doing any significant damage to the fabric of reality? Why would you want a device like this? It could compute faster. It could solve non-computable problems, for example, proving Goodstein's theory if you only have Peano arithmetic starting point, or automatically train, for example, large language models, because objective reduction will automatically find and train its model. During COVID, I decided to build one of these for a number of reasons, but I wasn't able to do anything else, and I built one in my garage. So this was the very first one we built. So this is an objective reduction experiment, and obviously I had to teach my children about laser safety because we had some lasers involved, but they're all intrinsically safe lasers, so double safety, which I explained to them. So the first question is, does the objective reduction part of ORCH-OR work? We all know the double slit experiment. Anyone not know the double slit experiment? I'm going to explain it anyway. You take a lamp, you put it through two slits, and you get an interference pattern. And that's because light has this wave property, and when the waves all line up, you get a bright light, and if the waves are out of phase, they sum to zero, and you get a dark patch, and so you get this pattern. So now let's put some shutters in front of these slits, and if I close one of the shutters, then I obviously just get a single line. In fact, what you do get is a single slit diffraction, so there's some tiny kind of fur to this line. If you try and look at the slits and say, I'm going to try and work out which way the photon went, you get two lines. You no longer get the interference pattern, so it goes away. So you can't gain knowledge of the individual pattern of the photons. So we proposed a thought experiment. Imagine I have a single photon, and it comes on from the left-hand side, and it goes into a beam splitter. Half the photon goes straight ahead, and half the photon goes north, and we'll just flip it around with a mirror just to make the diagram right, and then I'll put in an amplifier, a motor, and two shutters. And the question is, what happens? If the shutters are both open, I'm going to definitely get an interference pattern, so it's going to collapse. And the question is, where's the measurement made, right? In that experiment, do I put the amplifier and the motor and the shutter into superposition and therefore get a brief interference pattern? Now, the first thing people say is, you've got an amplifier in that. An amplifier is a detector. A detector is a measuring device, it's conscious, or whatever, it's an observer anyway. So we typed in Penrose single photon into Google, as you do, and came back with a paper by Quantvis, and he said, if you have a SPAD, which is a new type of single photon detector, it will not collapse the wave function, if Penrose is right, for 1,000 seconds. Traditionally, all these experiments were done with photomultipliers, which are big, weighty things, and now there are these incredibly thin film devices, and think about what happens to that mass. All that happens is it gets a little bit warmer, and the atoms move a very tiny amount when they detect a photon. So the actual difference in space-time between I've seen a photon, I have not seen a photon is tiny, which means if you do the calculations, you find that it actually would stay in superposition for 1,000 seconds. We replace the amplifiers with SPADs. They're not going to collapse. Now, obviously, the motor and shutters are. There's a Howell Fuentes Penrose paper, which says if you move by just an angstrom unit, what happens is that you get a lambda squared term, so you get 10 angstroms squared, which is an incredibly tiny number. That goes on the bottom of this equation, which means the time is very large. So you actually get 1 microsecond collapse time. So we built this, and I can show you what the trick is. We've got a laser that comes in here, and it goes into a half-silvered mirror. Half the photon goes north, half the photon goes east. They hit a mirror, they come back and they're put back together. So it's the same experiment as a double slit, except for now I have it go around corners of a square. So what I'm doing is changing the path length. Both mirrors will go into superposition, and as you see, both waves will change, they'll change the same amount. If you change the waves the same amount, the interference pattern does not change. What will happen is, for a while, it'll be in superposition, and so both waves have moved the same amount. And then after a little bit of time, one side collapses to the other, and it'll move. So you'll end up with a difference between the control and the superposition trace. So we published in February this year the proposal for this experiment, and so we do indeed get a difference in the control and the superposition. I was talking to Santosh Heligar in the bar last night. He's giving a very good talk which you should go to on Saturday morning, where he shows that if you have an interference device and you put it near someone's head, then it has less interference than if you put it away from something conscious. I thought, well, the only way that you could explain that would be if there's something in your head is crowding out space-time so it can't go into superposition. And then this morning I went, well, the only way to really explain his thing would be if collapse is quantized. Because if collapse is quantized and you've already pushed it halfway, it's only halfway it can go before it's going to collapse. So I ran the experiment through the obvious thing I should have run it through some time ago to see whether it is discrete or continuous. And we get a sort of quant effect. I have to do a lot more work to make a claim.
What's the frequency?
That's in megahertz. Then people, of course, if they've got a physics degree, go, decoherence will completely destroy your experiment. This cannot possibly be working at room temperature. You are delusional. But remember, the thing about decoherence is you lose the phase information. So the phase information in a density matrix, these off-diagonal terms, they go to zero. But you're left with a matrix which is a half, zero, zero, a half. It's a symmetrical equation. We need to go asymmetric. We need to collapse one way or the other. So we're arguing that this is like a Cheshire Cat experiment. We've separated decoherence, which shows one effect, which we're not bothering to measure. It's 10 to the minus 30 seconds or something. But we're looking at symmetry. So we're looking for symmetry breaking, and that we can measure in long periods of time. Can you run the experiment a different way? Yes. If you believe that thin film switches are not going to collapse, why not get a radio frequency thin film switch? They've got incredibly low amounts of energy, and pump RF into it and see whether you get the same effect. So here's a standard trace. So you have two photons come in. So here's the first photon came in, there's the second photon, and you get one antenna switches on, and the next switches on. That's what you would expect. But every now and again, you get this. You get two photons, one photon comes in, the other photon comes in, but you immediately rise to the position where both antennas have effectively switched on. And you would use that commercially to implement something like a quantum MIMO, where until the first receiver receives a signal, you have your signal in superposition, and once someone receives it, it collapses, and then the next receiver doesn't see a superposed signal, which means you get a sharp cell. What about the other part of ORCH-OR, which is the orchestrated part of it? Because you can't do this with just objective reduction. So I was at a conference in La Jolla quite a long time ago, and I went to the bar afterwards. So a lot of things happen in bars. Maybe I should, there's a problem there, maybe. And this guy came up to me and said, did you know that all the pictures that you see of microtubules are wrong? And I went, no. He said, they're not cylinders, they're furry. They have tons of fur on the outside of them. So I thought, well, that's really interesting, because I've been looking for something like that for a long time. So they have this complex tail of proteins that are attached, and after the microtubule gets minted, these complex proteins then react in all sorts of ways and extend and cross-link and so on, and they make about 100,000 different proteins that are on the outside of the microtubule. So there's kind of flora and fauna living on the outside of microtubules. I said, this is exactly what I've been looking for. Here's an idea of how you could put it all together to make a quantum gravity computer. What do I need as an engineer to make one? I need signals, I need wires, I need gates, logic gates that will compute in some way. I need to control those gates. I need the gates to actually do something when I ask them and do different things. And then I need to amplify up from the sort of microtubule layer to the neuron layer, because my finger moves because my neuron fired, it does not move because a microtubule told it to. It has to get from one place to the other. And if you take all of the sort of talks that we've had and you plug in this tubule and tail idea, you have maybe a plausible argument for how it might work. So you have the biophotons that Travis Paddock and Jack Szynski and various others have proposed. So you can do photonic computing. Your wires are the microtubules, where the tryptophan gives them radiant or ballistic transmission. This energy is absorbed by post-translational proteins in the microtubules, at least in the tails of them, that cause those to move. Now we know that this happens in the eye, for example, so it's not outlandish that we have a photon absorbed and then a move. So there's my gravitational piece. I need something to actually move and move some mass. Ideally not enough to immediately collapse it, but enough that in conjunction with other things it could collapse it. And then I can have more than one opsin involved in a tail, so I can build C0 gates and CC0 gates and all sorts of things I need to do in quantum computing. And then finally, it's known that these tails, some of these tails connect to the ion channels of a neuron and are involved in causing the neurons to fire. So I've got a way by which I can get from the sort of microtubule scale up to firing a neuron, or at least making the neuron fire faster or slower. And of course, I'm an engineer, so I'm trying to build this in not a wet lab, but a dry lab. So I'm doing it with photons and waveguides and micro machines, silicon and all those sorts of things, and the SPADs we saw earlier. So that was my sort of motivation. Nice thing about the brain, of course, is all floating around, right? Sort of in zero gravity, in water. We have to think about making our little devices suspended on strings or springs or something so that they can not be in certain positions, because we want uncertainty in the space-time distribution of our gates. But that's the trick. So that's what I've been doing for the last couple of years. Okay, we're exactly on time. We've been told we can have a tiny bit more time. So, any questions, or do you want to hold questions until the end? I had a discussion in another bar last night, and what we were wondering was whether you could put in some sort of cranial ultrasound or transcranial magnetic stimulation to cause the fur to vibrate or lie down or stand up or something like that, and that would cause exactly what you're suggesting, would either speed it up or slow it down. I think I've got an invitation on Friday to go over to the lab to see whether we can find an appropriate frequency that might do that. Yeah.
Comment and then a question. Comment, let's go to the bar later.
Yeah, thank you.
And a question. The collapse you're seeing in your experiment has a sort of tentative positive signal.
Yep.
Are you're interpreting that as a collapse between the state of the mirror recoiling?
Well, the photon has to be in two places at the same time, so it has to be in superposition, and then it triggers the mirrors in superposition, which then are illuminated with some other photons that allow us to read out the fact that it's in two places at the same time.
Got it. So then, if it's the mirror displacement, how come this doesn't have to be done in like a vacuum to stop the...
You're right, and in fact we did actually buy vacuum stuff, and we did book a space in the vacuum lab at UCSD to do this, but unfortunately when COVID came, they shut us out of that for 2 years. So we'll do it at room temperature. It won't work, but at least we'll learn. We might as well build it and see what happens. And then we did get a signal. So we ran a bunch of things and we got a signal. And our statistics guy said, well, okay, it's small, but there is a difference. We went, oh. And then we ran around the sort of physics community asking how on earth could this be, and came up with this idea that you separated collapse and decoherence. So it's decohered, it decohered in 10 to the minus 30 seconds, but for you to actually break symmetry and one side fired and the other side gives up, whatever sort of explanation you want, it's got to break symmetry, and that's not decoherence matter. That's nothing to do with decoherence. Although 19% of physicists, when questioned in a survey, said that it was decoherence, but that's wrong. If you watch that Sabine Hoffenfelder video. Yeah.
It sounds like there's going to be an after party at the bar.
Yes.
I was curious, a couple of factors. In quantum computing and now when these two are starting to come together, have an application from
I'm fascinated. I don't know enough about the sort of quantum annealing type quantum route to make advances personally, but talking to someone who does would be really great. Okay, shall we go to the next speaker? Thank you very much for your questions.